Okay, so today we're going to start on probability, but first I do want to wrap up the stuff on recursion, in particular unfolding on the binary search. So technically you have everything you need to finish your assignment, but we will look at unfolding one more time, and then we'll review all of the important things that you should know from recursion for the midterm, and then we'll start probability. And so I'm thinking everything we take in today's class is fair game for the midterm, and then next Monday, that I will leave that off. So yeah, I'll have to search through very carefully to try and find them, but that's the idea. However, uniform probability and probability are basically the same thing, so you shouldn't have too much trouble. There's not really that much difference. Everything we're going to take today is actually, well, most of it's going to be uniform probability anyway, but all right. Any questions before we get started on the schedule, or quick questions on the assignment? Okay. So let me get set up here. So it turns out the analysis of binary search, was more or less correct, except it was just messier than I expected. There's a weird edge case. So yeah, so just a quick review of the binary search algorithm. Let's say we have a sorted list, and yeah, so let's say we have a sorted list, and then we want to search it, and we're searching, for instance, for 17. So we start by looking at the midpoint, and we see that the midpoint is 14. Well, 14 is less than 17, which means that 17 has to be to the right of 14. And that means we get to ignore all of this part of our list. And there are, in this section, there are n over 2 ceiling, right? So this is actually a list of odd length. So that means when we do the recursion, we're doing it on n over 2 floor function, right? So that means if the list can be split evenly, then it's possible we end up with n over 2 items left to search. Otherwise, we're going to be left with essentially n minus 1 over 2 if n is odd. So that'll come into play later. So for now, we look at the midpoint again, the midpoint being, in this case, the ceiling of n over 2. 17 is less than 22, so we know that 17 is in this section, and we can basically ignore the rest of here. And then we go to the midpoint of what is left, and we find 17. And so we found 17 in 3 comparisons, and that's essentially the binary search algorithm. So here it is in pseudocode. And so what we want to count is memory accesses. If you could read my scratch. So memory accesses in particular are this line here. So what that means is that every time I call binary search on a list of length at least 1, then I do exactly 1 memory access. And then I do a bunch of comparisons and stuff, which we could also count, but we're not going to in this case. However, if I pass in a list of size 0, that would be this case. And what happens is I do 0 memory accesses. I do 1 comparison, and then I return. So t of 0 is equal to 0 is one of the base cases. And I should add, actually, t of 1 equals 1. So there is sort of this, there's 2 situations. Either I find the thing I'm looking for, which is we end up in this case, or the item I'm looking for is not in my list, and then this is the base case. So in a sense, we kind of need both of them. And then my recursive case is, well, if n is greater than or equal to 1, if n is greater than or equal to 1, then I do, let's make that 2. And if n is greater than or equal to 2, then what happens is I do 1 memory access, which is here. And then I do one recursive call, either on the left-hand side of the list or the right-hand side of the list. So that's this T of n over 2. And I'm going to use the inequality here because of what we talked about before, how, it might be n over 2, or it might be, if n is odd, it can be n minus 1 over 2, or the floor function of n over 2. So we're going to use an inequality just to keep things a little bit cleaner. So the main purpose of this exercise is the unfolding. Typically, when we give you, if we give you something to analyze, an algorithm to analyze, this will work out cleanly, right? So you can use, generally speaking, you can use equals. Yeah, if you have to use an inequality, that's fine, but that probably means I made a mistake making it. Okay, so now at this point, we have a recursive expression, and now we want to use unfolding to find a pattern. So what we want is a closed form. Closed form means we express T of n in some function of n that does not involve recursion. So to use unfolding, we take, we're going to take T of n over 2, and we're going to substitute n over 2 into our original equation. So we get is less than or equal to 1 plus T of, and n over 2 is n over 4, right? So we're going to take this equation, and then we're going to substitute for T of n over 2 this expression. And then we get 1 plus 1 plus T of n over 4. And then T of n over 4, what we can say is less than or equal to 1 plus T of n over 8. So, and T of n over 8 is actually T of n over 2 cubed, right? So this is 2 squared, and this is 2 cubed here. So 4 is 2 squared, and 8 is 2 cubed. So we can kind of see a pattern emerging. So I wrote n over 2 cubed here. So now when we analyze our pattern, we can see that, well, we have the same number of ones as our value here, our exponent for the 2's. So that makes, the final form sort of easier to express. So we can say we have k ones plus T of n over 2 to the power k. Okay, so now we found a pattern. Now we have to find where our recursion ends, which our recursion ends at T of 1 or T of 0. So if it's T of 1, what happens is, then we have n over 2k is equal to 1. And then if we do a little bit of algebra, we get, n is equal to 2 to the power k. We take the log base 2 of both sides, and we get log n equals k. So we can solve for k to find our base case. And then it's possible that, so our base case is T of 1. We know that T of 1 is equal to 1. So let's actually write that out a little more explicitly. So this is less than or equal to k plus, so this would be, sorry, what did I put here? K plus T of 1, which is less than or equal to k plus 1, and then plus T of 0. T of 0 is 0, so we are simply left with k plus 1. So it's a little bit messy in the edges, but ultimately we arrive at this place where we get k plus 1 plus T of 0. T of 0 is equal to 0. And and then we can solve for k. And so we get T of n is less than or equal to log n plus 1. So we substitute log n for the k, we substitute 0 for the 0, and then the 1 just stays the same. All right, so then we have a guess at the closed form for this recursive recurrence. All right, questions so far? Okay, so here's what we know. So we obtained these by analyzing the algorithm. Okay, so these we know are true because we we came up with them, we verified it. Now we want to prove that our closed form that we came up with using unfolding is true. So how we do that is using induction. So our base case, we will ignore, we're going to assume for our base case that n is at least 1. So you've passed in a list, it has at least one element in it. The problem is for n equal to 0, log base 2 of 0 is not defined. So again, binary search is a little bit messier than I expected. It still works, but now you have to sort of explain a bunch of edge cases. Yeah, so our base case, 1 plus log base 2 of 1, well, log base anything of 1 is equal to 0. So I end up with 1, which is what my base case is. So our base case holds. Now our inductive hypothesis, we will assume that this is true. Right, that t of n over 2 is less than or equal to 1 plus log of n over 2. So now we're going to use that to prove that t of n is less than or equal to 1 plus t of n over 2. So what we do is, since we're assuming this is true, we can substitute this in for this, right? And so we get 1 plus log of n over 2. Log of n over 2, I believe we talked about, is equal to log of n minus log of 2, and log base 2 of 2 is equal to 1. So we get 1 plus log of n minus 1. This becomes, the log base 2 of 2 becomes 1. So one of these ones cancels out with this, and we're left with 1 plus log base 2 of n. Okay, so then we've shown that, we've proven what we wanted to show, which is that this is the closed form of this recursion using induction. Yeah, so we don't need to show the base case of t of 0 working with our formula. So it's helpful to remember what exactly we're trying to prove. So I could, for instance, make the assumption that our item is in the list. And if I make the assumption that our item is in the list, then I don't need that base case. And then that's probably what I should have done, and then everything would be clean. But if I assume that maybe it's not in the list, then I end up with these messy edge cases. So what I'm essentially saying is that, well, even if the item is not in the list, we still end here. But yeah, but now I have to, I guess my closed form also must include this, which is, so if n is 0, I have this, and if n is greater than or equal to 1, I have this, and that's it. Yeah, in hindsight, I should have just made the assumption that the item we were looking for was in the list. All right. Other questions? Okay, so that is, so that, and along with the merge sort, are your, 2 examples of using unfolding on a recurrence in order to get to a closed form. So you should understand how to do that. But let's go into things to know about recursion. This is, let's say for the midterm. So you should know how to prove a closed form of a recursive function using induction. So that example we did, we actually showed that, but of course I could give you, something independently, like equals n times f of n minus 1. I'll say that's my recursive function, and then I want you to prove to me that f of n is equal to n factorial using induction. So this is given, and this is to prove. So those are kinds of questions you should expect. Also, know how to map a problem to the Fibonacci sequence. It is possible that there should be an extra n in there. Also, you should understand the Fibonacci sequence, right? So this idea that f of n is equal to f of n minus 1 plus f of n minus 2, there's a lot of implications there. So any problem that maps to this sort of recursive form, in some sense, yeah, there's a lot of patterns there that you can take advantage of, right? So a lot of questions might ask you, well, I mean, if you look at the, right, so I might ask fib 77. So how many times is this called? Right, so I might give you some pseudocode algorithm of the Fibonacci to compute the Fibonacci numbers, and I'll ask you, how many times is this called on a call to fib 100 or something like that? So you should understand how to get those numbers. I'm not going to give you a complete example here because there are complete examples in the midterms from previous semesters. How to analyze a recursive algorithm by finding a recursive function, right? So I give you some pseudocode and I say, well, it's the same as in the assignment, right? Count how many times we call this function process. So you should be able to analyze that in a recursive algorithm. And how to use unfolding on a recurrence to find a closed form. Right, so you should be able to take a simple recurrence, unfold it, find the pattern, and find a closed form for it. Okay, so those are probably the most important points that you should know about this chapter on recursion. Okay, questions? All right. So we will start on probability. Now, the first example on probability is somebody asked in the last class, what is this? Why are we taking this? And I didn't really have a good answer. So we're going to look over, so in general, we're going to, of course, figure out how to compute probability of events happening. But we open up with an exercise and it's from the textbook. So it probably becomes important down the line in a way that I'm just forgetting right now. But yeah, in sort of the immediate sense, we're going to take up an example that's interesting in the sense that we can use randomness and probability to do something interesting that doesn't seem to be related to randomness and probability, right? So in this case, we're going to use it to hide information. But yeah, so I'm going to try not to get too bogged down in the details. There are a lot of details. Just know that if you don't follow every detail, that's okay. I know that later in the semester, we come back to the idea of using randomness to prove things that aren't even random. So this might be an introduction to that, and I'm just forgetting. Yes, so the midterm is multiple choice. So there's 17 multiple choice questions. Will probability be on the midterm? Yes, everything you see up to the end of this class will be on the midterm. I might have to trim some questions. So there's 17 right now. And then I might either trim some questions or just simply add in more counting and recursion because I think there's some questions on there that we're not going to get to, or we will get to maybe next class, but then I don't know. It's a bit of a quick turnaround to try and understand these concepts. No e-proctoring. So yeah, I trust you guys. But there's a lot of privacy issues there, right? So these sorts of, so of course it's open book. So use the slides, use the textbook, use your own notes, whatever. You can even use the old midterms if you and the answer key, so you won't find the questions. The questions that you will see won't be on those, but you'll see similar questions. So you can use all of those resources, and yeah. Otherwise, the only thing we can do, I can't even verify who actually writes the midterm, but the only thing we do is it is a timed, right? So you have to be here during class to write it unless you've made other arrangements. And that's how we sort of keep the lid on things like collaboration, because everybody does not have enough time to reach out to everyone. We use any resources on Brightspace, just don't Google or something, right? Yeah. What should I say about Google? There's no way for me to know if you're using Google. Let's say that. I don't know. Yeah, I could refuse you, and then some people would use it, and then other people would have an unfair disadvantage. The questions are selected in a sense that probably your best resources are either the notes or the textbook, or the old midterms. So Google, you could try, but I doubt it's going to be as successful as just having your notes organized in front of you. All right, any other questions? Yeah, no problem. And yeah, so like I said, you do have to show up unless you make other arrangements, you have to show up at this time to write it. Tailored so that we don't really need anything. Well, as I said, you could try Google, but I think the textbook and the notes make better resources. That's all. If you've had success on the assignments Googling for answers, then maybe, you still have to sort of understand you're never going to find the answer for these. Well, of course there's ways to cheat. Anyway, you'll never find these through a Google search, but even if you do a Google search, you still have to understand the technique they're explaining, right? So it's really not going to help you any more than any other resource would. Yeah, so yeah, and do show up. I know I'm going to get some people that are like, oh, I forgot, I didn't know. But yeah, not you guys, because you guys show up, but there's a lot of other people that. All right. We have an hour 30. Yeah, I think so on Brightspace, and it's going to be, maybe I'll give you an extra 10 minutes, because I know on Brightspace you can only do intervals of 10 minutes, which means it's going to start at 8:30 instead of 8:35. And then I think I have it ending at 10, but I'm going to move that to 10 after 10. And then, some of you have PMC exemptions and things like that. That will be handled by the PMC. I don't do that. So they will adjust your midterm for you. So do reach out to them. If you have those exceptions, reach out to them to make sure that they're done. Yeah, the midterm 17, as I said, I might have to trim some, but we'll see. So it'll be at most 17. And they're multiple choice, and do look at, if you want to get an idea of what they're like, do look at the old midterms. All right, other questions? Okay. Probability. So I like this one because there's lots of interesting things you can do with probability. A lot of games involve probability and I guess gambling, but you shouldn't gamble. House always wins, as you will learn, but it is interesting to analyze it to see how badly you're going to lose. So yeah, you may have seen some probability, but we're going to redefine everything from first principles using sets and counting and things like that. So in this example, so for instance, something you may have taken before, of course, if you flip a coin, it comes up heads with probability 0.5 and tails with probability 0.5. Although you probably see it expressed as, heads with a probability 1/2 or 50% or something that's equivalent. So the other thing is if I flip a coin and I put it behind my back and don't show you, and you tried to guess if it was heads or tails, you would not be able to guess. You would only have a 50% chance of getting it right? So yeah, that's sort of obvious, but it relates to this problem that we're going to see here. Again, this problem is not directly related. It's an introduction to this topic, but the stuff that you will see is more of a, hey, that's cool. It's not going to be, you won't be tested on these things. I'm going to teach it anyway because, well, it's part of the textbook, and I'm thinking maybe I'm just forgetting that it relates to something down the line. So I'll teach it anyway. So we have a group of people on a network. We want anyone to be able to broadcast. However, so we want one person to be able to broadcast a message. Everyone receives the message, but the big catch is nobody knows who sent it, right? So we're going to disguise the sender of the message using basically coin flips. So in this example, they talk in binary, so we're going to transmit one bit at a time, either a 0 or a 1. Okay, so we have, and to keep it simple, we'll use a network of 3 people. So this is sort of the minimum number of people you need for this example. And one of them will broadcast one single bit B that's either a 0 or a 1. Okay, so then here are all the things that we just explained so that you can reference back to them. Yeah. Sorry, is there a question or just somebody's mic going off? It happens. Okay, so they transmit one bit at a time. One of them broadcasts a 0 or a 1, and we want to hide who sent it. Okay, so we have P1, P2, and P3. They're all on some network. It's a circular network. Let's say P1 broadcasts a bit B to P2 and P3. So they're going to send out some information. You know, maybe you're part of the French resistance during World War II and you want to hide your location or something. Although, of course, that predates the internet, but all right, so one broadcasts a bit. So the protocol we're going to use is that every person flips a coin. So person PI has a random bit BI. So P1 has B1, P2 has B2, and P3 has B3. Each of these shows their bit to their clockwise neighbor. So P1 is going to show B1 to person 2. Person 2 is going to show their bit to person 3, and person 3 is going to show their bit to person 1. Now, person 1 is going to compute a bit S1, which is B1 plus B3 mod 2. So person 1 knows this bit. Person 1 knows this bit. Yeah, person 3 showed them this bit. So they're going to add them together modulus 2. Right, so these are, so what precisely does that mean? Well, if I have 0 plus 0 mod 2, that's equal to 0. If I have 0 plus 1 mod 2, then I have 1. And if I have 1 plus 1 mod 2, then I have, of course, this is 2 mod 2, which is equal to 0. So when I do the mod 2, and I sum up these bits, I really just end up flipping them either to a 0 or a 1, depending on depending on the situation. Okay, so each of them is going to compute, so S1 for person 1. Person 2 computes S2, which is the 2 bits that they know about. They will sum them together, mod 2. And person 3 computes S3, which is the 2 bits that they know about. And in our example, we're going to assume that P3 is the broadcaster. So P3 has a bit B that they're going to, well, we'll see in a second. So if for all of the people that aren't broadcasters, they compute their transmission bit and they simply set it equal to their S bit. So, and if they are the broadcaster, then they take their transmission bit and they add B to S and mod 2. So if B is a 1, then they flip this bit. If B is a 0, then they keep it the same. All right. So yeah. So person 2 computes T2 is equal to S2, and person 3 computes T3 is equal to S3 plus B. Okay, so one thing that I do go over this a little bit later, but I wish I would want to introduce it earlier. But if I do B1 plus B1 mod 2, this is always equal to 0, right? So if B1 is 0, I get 0 plus 0 mod 2. And if B1 is 1, I get 1 plus 1 equals 2 mod 2 is equal to 0. So anytime I add a bit with itself, modulus 2, I get 0. Okay, so then what happens is, and the other thing, if I do, let's say B1 plus B2 plus B3 mod 2, that's the same as saying B1 plus B2 mod 2 plus B3, and then that whole thing mod 2. So the order that we do the mod 2s doesn't really matter. So if I have a value that I've computed mod 2 and I add it to another value that I've computed mod 2, it's the same as if I've added all the original values and computed them mod 2. Okay, so all of that being said, oh yeah, the TI is the transmission bit. So this is TI is a transmission bit. So once they all compute their transmission bit, then everybody broadcasts their transmission bit to everyone else. And then each person computes sums up all the transmission bits mod 2. And then what happens is, so that's equal to S1 plus S2 plus S3 plus B mod 2. And then if I break down all of the S1 plus S2 plus S3, well, I get B1 plus B1 plus B2 plus B2 plus B3 plus B3 plus B. And that evaluates down to B for the reasons that we described earlier, is that any bit plus itself mod 2 is equal to 0. So these all become 0, and then all we're left with is B. All right, so other questions? Okay, so for example, let's say everyone flips their bit. Again, we'll have P3 broadcasting, but P1 gets a 1 by, just by flipping a coin, they get 1. P2 gets a 0 and P3 gets a 1. Now we're going to show B3 gets showed to person 1. They compute B1 plus B3, which is 1 plus 1 mod 2, which is equal to 0. Person 2 computes S2, which is B2 plus B1. B2 is 0, B1 is 1, so that's equal to 1. And then S3 is equal to B3 plus B2. B3 is 1, B2 is 0, so that's equal to 1. Now, the transmission bit, so P1 is not broadcasting, so it's the same as S1. Person 2 is not broadcasting, so it's the same as S2. Person 3 broadcasts a bit equal to 1, so they're going to flip this 1 to a 0 for their transmission bit. Okay. Now everybody broadcasts to everyone, and then we sum up T1 plus T2 plus T3. So that is 0 plus 0 plus 1, which equals 1, which is equivalent to the bit we were trying to transmit. So that's one example of anonymous broadcasting. But go back a bit. Yeah, to which part? The previous slides or? number 7. Do I have a number? Are these numbered? This slide? Oh. All right. Just let me know when you're finished. All right. Yeah, I know. These are dense slides. Yeah, I may change this example for if I teach this class again in the future. Start with something a little bit lighter. Okay, so we've run through an example. We've seen, in this case at least, it appears that this works. We reveal the bit B by adding all the transmission bits. Now we simply want to show that, so we can, perhaps you're convinced that we can transmit B this way. The only thing that's left to show is that P1, for instance, can't determine if P3 or P2 was the one to broadcast it. So that's what we have left to show. Here I sort of reiterate why this works for any bit, because if I take 2 bits and add them, I always get 0. So yeah, that means I take my B1 plus my B1, that's equal to 0, B2 plus B2 is equal to 0, and B3 plus B3 is equal to 0. And then all that's left is my B. Okay. So, and what information is being broadcast? Yes, so the idea is, so we can broadcast any information 1 bit at a time. And generating the random bits sort of helps us to hide who broadcasts the information. What information is being broadcast? Anything you like, anything that you can encode as a bit string, which is basically anything, right? But, you know, so I could send you, for instance, a song, but I would have to send it 1 bit at a time. You know, for instance, if we were on a torrent network and I was trying to, you know, illegally send something out and I wanted to hide the fact that I was sending it out, then we could, you know, mask it this way. So then, you know, everybody sends out a bunch of information and everybody can collect the information and download the song illegally or whatever it is. And then nobody knows who broadcast it. So that's sort of the idea behind it. It's to do illegal stuff. So yeah, so now we want to show that we can broadcast a bit this way. That seems, hopefully seems a little clear, but we want to broadcast anonymously. So how can we prove that? So it's, perhaps you have an intuitive understanding of this problem, and if so, great. Otherwise, we're going to turn to our friend brute force. So we're going to look at a bit of a case analysis. We're going to examine some cases and see what happens and why we can't identify who broadcast. Okay, so we're going to assume that the bit we're broadcasting is a 1. We're going to assume that P2 is not the broadcaster. We are going to be P2. We're going to try and figure out who broadcasts the bit. So P1 or P3 is the broadcaster, but we don't know which one. So we're going to look at all of the information we have and see if we can determine who is the broadcaster. So actually at the end, after everyone is broadcast, we can figure out maybe, no, sorry. These should be the T1s. T1, T2, and T3. So we know T1, T2, and T3. And we know B1 and B2, but we don't know this 3rd bit. And so we don't know B3 and we don't know who added the bit B to their broadcast. Okay, so yeah, these should be, sorry, these should be T. Okay, so yeah, these parts are unknown. So we know B1 and B2, so we know the thing that we broadcasted, but we're trying to figure out this part and who put the bit B in their broadcast. Okay, so case one is if, so the two bits that I know, B1 and B2, let's assume that they're the same. They're either both 0 or both 1. And then let's assume that B3, which we don't know, is also the same. Well, if P1 broadcasts, then we get T1 is equal to 1 and T3 is equal to 0. If P3 broadcasts, then we get T1 is equal to 0 and T3 is equal to 1. So if this is the case, then we can figure out who broadcasts by T1 and T3. However, we don't know B3, and it could be that B3 is not equal to B2 and B1, in which case, if P1 broadcasts, T1 is 0 and T3 is 1. And if P3 broadcasts, then T1 is 1 and T3 is 0. So that is to say, if we see that T1 is 0 and T3 is 1, then we know we're in one of these cases. But since we don't know B3, we don't know if we're in this case P1 broadcasts or this case where P3 broadcasts. Okay, I know this is there's a lot of bits, they're dense slides. I feel like it's, anyway, we're committed to it now, but in the future I'll probably try and get a better example. Or perhaps we know that T1 is 1 and T3 is 0. Well, then I know I'm either in this case where P1 is broadcasting or this case where P3 is broadcasting. But without knowing B3, I can't figure out which case that is. Yeah, so case two, let's say I know B1 and B2, those are the two bits that I know, but let's say they're not equal to one another. Well, if B2 is equal to B3, then I have T1 equals 0 or T3 equals 0 if P1 broadcasts, or I have T1 equals 1 and T3 equals 1 if P3 broadcasts. Or I could have B3 is equal to B1, in which case T1 and T3 being 0 is if P3 broadcasts. So again, I know these two values. So I know I'm in this case or this case, but because I don't know B3, I don't know if P3 was a broadcaster or P1. All right, ugly, ugly case analysis. And likewise, if I know that T1 is 1 and T3 is 1, then I know I'm in one of these cases, but without B3, I cannot figure out which it is. And yeah, on the other hand, if B is 0 and P2 is not the broadcaster, then we end up in a case like this, where I know T1 and T3 are 0, but I don't know if I'm in this case or this case. And the same for if T1 and T3 are 1. Just arrest them both. Yes. Send everybody a scary warning through Rogers that says, we know you downloaded that movie. All right. Any questions? I know it's really dense, so I don't know. Like I said, this is supposed to be sort of a nice introductory example, and I think it falls a little short. Okay, so, and then we can transmit any amount of information this way, right? So all I can do, I just do it bit by bit to transmit a longer string. So yeah, I'm safely on my BitTorrent network, uploading some illegal movie or song or whatever, and nobody can figure out who it is. Okay. All right. So that's, yeah, that was the nice light introduction to probability. And the interesting things that you can do using randomness and probability, right? So we can mask these things from snooping federal authorities. Okay, so probability. So we're going to now get into officially the this part is actual information that you need to know for instance, for assignment 3 and a little bit of the midterm. So to start with, we have a set S. That's a non-empty set. That is called a sample space. So we'll see exactly why it's called that in a minute. So for instance, this is our set S, and I have a T, a heads and a tails in here in my sample space. So these are two, the T and the H are known as outcomes. So each of the elements of my sample space is known as an outcome. So for example, if I flip a coin, my sample space is heads or tails, and the outcomes could be, well, I flip a head or I flip a tail. So, okay. Now a probability function, PR, is what we'll use to represent it, maps all of the elements of the set S to the real numbers such that for every element of S, it's a number between 0 and 1, right? So for instance, so my probability of W could be 0.5 if I'm talking about the probability of flipping tails or heads on a fair coin, right? So I'm going to have some number. It could also be, I suppose, although this would be pointless to have in your sample space, you could have a probability of 0, and you could have a probability of 1, which means that it always happens. But the other attribute of my sample space is that all of the probabilities of each element must add up to 1, right? So for example, my probability of getting heads is equal to 1/2 or 0.5. My probability of flipping tails is equal to 1/2. And if I add up the probability functions of every element in my sample space, well, I get probability of heads plus probability of tails equals 1, right? So everything in my sample space, all the events must sum up to 1, all the probabilities of each event. Okay, so what that means is that basically something from my sample space has to happen by definition. You know, so I'm doing some experiment, I'm looking at the outcomes. Each outcome is represented here. Something must happen though. I can't just have nothing happen unless I make nothing an event in my sample space and give it a probability. Okay, so the probability function assigns a real number to each element of S, and all these numbers summed up must equal to 1. So probability 1 means it's definitely going to happen. So that means if we select an element from the sample set S, or the sample space S at random, we do so with the probability defined by the probability function. So selecting an element from this sample space, each of them has probability 1/2. However, maybe we have a different sample space, some arbitrary sample space where we have elements W1, W2, W3, W4, and we can assign probabilities to them according to our rules of the probability function. That is, each must be a number between 0 and 1, which those are all fine. And then if we sum them all up, they must sum up, they must sum up to 1, right? So I can assign, these don't all have to have the same probability. They can have different probabilities as long as it obeys these rules. All right. Questions? Okay. So let's look at an example, the same example as before. We have a sample space S. So our trial is going to be flip a coin, or our experiment is flip a coin and see if it comes up heads or tails. So our outcomes could be heads or tails. So if the coin is fair, then the probability of flipping heads is 1/2, and the probability of flipping tails is 1/2. And that sums up to 1. Or we can have an experiment where we flip a fair coin twice in a row, right? So then we have to look at all the possibilities. Well, our sample space now is the result of flipping 2 coins, right? So I could have flipped heads, heads. I could have flipped heads, tails. I could have flipped tails, heads, and I could have flipped tails, tails. So these are all possible outcomes of my experiment. In this case, again, each outcome may happen with equal probability, since this is a fair coin. So that means probability of heads, 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 tails, tails, heads, and tails, tails are all 1/4, which means if we sum them up, they all sum to 1. So this would be an example of my sample space for flipping a fair coin twice in a row. Okay, so that's sample spaces and outcomes. Any questions? All right, so now we're going to talk about events. So events are very similar to outcomes, but event is just a subset of the sample space, right? So here is my sample space for flipping a fair coin twice. So maybe I have an event A that I define as I flip exactly 1 heads and 1 tails, right? So this does not count. So yeah, sorry, let me get to, all right, we'll get to that later. So yeah, in my my event of flipping 1 head, 1 tail, I have these 2 elements. So the probability of an event is the sum of the probabilities of each of the outcomes in the event. So I would take the probability that A happens, some event, is equal to the probability of this plus the probability of this. So yeah, I take each element in my subset A and I sum all the probabilities to get the probability that event A happens. All right, so if I flip a fair coin twice, and the event A is that I have 1 head and 1 tail, then my sample space is, of course, all of the possibilities, and my event A consists of heads, tails, and tails, heads. Right, so now my probability of event A happening is my probability that I flip heads, tails, plus the probability that I flip tails, heads, which is 1/4 plus 1/4 is equal to 1/2. All right. Questions? All right. Let's take another example. I roll a fair 6-sided die, right? So that means I have the numbers from 1 to 6 on different faces of my die, of a cube. I roll it, and with equal probability, I get the numbers 1 through 6. Okay, so now my sample space for rolling 1 fair die is the numbers 1, 2, 3, 4, 5, 6. These are all the possible outcomes of rolling my die, right? Something like this. So this probability function, if I sum all the probabilities of every outcome in my sample space, they all sum to 1. So I have the 2 rules. The one must be a number between 0 and 1. The other rule is it must sum up to 1. So this, this is a good sample space. Oops. So now we can define events in my sample space. Event A is we rolled an odd number. Okay, so our odd numbers are here. So this is our event A. So the probability that I rolled an odd number on my 6-sided die is, well, my event A consists of 1, 3, and 5. And if I sum up the probabilities of each of these individual outcomes, I get probability of A is equal to the probability that I roll a 1, plus the probability that I roll a 3, plus the probability that I roll a 5. So that's 1/6 plus 1/6 plus 1/6 is a 1/2, right? So that's what you would expect from rolling a fair die, is if I say, well, what's the probability that it comes up odds versus the probability that it comes up even? Well, they should be half each, since there are half the numbers are odd and half the numbers are even. Okay, good. Questions? All right, so then the same as we did with our heads and tails, let's roll 2 dice now. We're going to roll a red die and a blue die. So now our sample space is going to be the set of all pairs I and J, where I and J are numbers between 1 and 6, and I represents the red die, J represents the blue die. All right, so now if I list out all the elements in my sample space, I would have to do something like this. I could say, well, maybe they're both 1, or maybe the first one is 1, the second one is 2, or maybe the first one is 1, and the second one is 3, and then down to 6. And then I could start on, well, what if the first one is 2? Well, then I have to go through them all again. So I can list out all the events in my sample space as these pairs of numbers between 1 and 6. So yeah, what is the size of the sample space then? What do we think? How many elements are in this sample space that I started to draw, but I didn't finish? 36, yeah, exactly. So if I drew it as a, let's say if I drew it, well, there's a couple ways to do it. I could draw it as, of course, a table, right, that has 6 rows and 6 columns, and then 6 by 6 gives us 36 entries. I don't know how many that is, but it's definitely not 6, but you get the idea. The other way we can count it is using the product rule, right? So I can break it down into 2 tasks. I roll my red die as my first task. I roll my blue die as my second task, and I have 6 choices for each of them. So using the product rule, I can say that, well, 6 choices times 6 choices gives me 36 numbers. All right, so both of those are sort of valid ways to look at it. You can either list it out in a way that makes sense, or use the product rule. We will be leaning towards using the product rule to in order to count our sample space. Oh yeah. So then each of these has each of these outcomes has an equal probability of occurring. So that means each of them has a probability of 1/36. Right. So if I made a table of my red die and blue die, and I could list, so this is 1, 1, this is 1, 2, etc. Of course, if I roll 2 dice, then one of the exercises I like to do is probably sum them up, right? Generally speaking, I roll 2 dice, I add them, and then I get the total of whatever's facing on each of them. So then instead of filling this in with 1, 1 and 1, 2, etc., I could fill it in with the sum of these. So I have 1 plus 1 is equal to 2. I have 1 plus 2 is equal to 3. 2 plus 2 is equal to 4, etc. Right? 6 plus 6 gives me 12 if I follow the rows and columns. So here I have a table of the sum of each roll of these 2 dice. Yeah. Okay, so now I can define events. So and I have 36 entries, right? So each of these happens with a probability of 1/36. every single entry in my table. So now I can define an event such as, well, what is the sum? If the sum of the red and the blue die is 4. Okay, so I can go into my table and I see, well, the sum here is 4, the sum here is 4, and the sum here is 4. And, you can quickly spot the pattern. Most likely is that each of these numbers occurs in some diagonal across my table. So these are all of the values for. So then what do I expect is the probability of this event? What do you guys think? 3/36, yeah, exactly. So I just take each of these has a probability of 1/36. My event A consists of these 3 outcomes. So I just sum them together. So yeah, each of these is an event that is the sum of the red and the blue is 4. There are 3 of them. Each of them has a probability of 1/36. So I get 3/36 or 1/12. Okay. Everybody get that? Is there any questions? Okay. Makes sense. Perfect. So that's the sum of the red and the blue die is 4. What if we have event B, the sum is 5? Well, what do we expect our probability to be then? So we can go over to our table and we can, of course, count all of the 5s. So there are 4 of them. Each of them occurs with a probability of 1/36, right? So yeah, these are the 4 possible outcomes in my event B. So yeah, the probability of B is the probability of each of these summed up, which is 4/36 or 1/9. So yeah, you can easily compute the probability of any dice roll you want on 2 dice. I guess one thing you might notice is that the sort of longest diagonal is across the middle. So the 7s, rolling a 7 is the most likely of any of the numbers in the table. Specifically, there are actually 1, 2, 3, 4, 5, 6. So 6/36. There's a 1 in 6 chance of rolling a 7. All right. Okay. So a couple of other things that we can, some of the edge cases, we talked about events and outcomes, but for instance, if we have a set S of some bunch of the outcomes, we know that if we take all of the items in S, that is a subset of S. So S is a subset of itself. So we can define an event that is the all of the outcomes in our geez Louise, in our sample space. So if we sum up all of the probabilities of all of the events in our sample space, we get 1. So yes, S is an event and it has a probability of 1 of occurring, which means that something must happen. What is the probability that something happens? The probability is 1. Likewise, the empty set is also an event. Right, so if I have a bunch of items, but then I take the empty set as a subset, so I have this is a subset of S. So what's the probability of the empty set? What do we think? So probability of the null set, 0, yeah. So the probability that absolutely nothing is selected from S is 0. So basically by the way that we've defined our sample space, right? So we've defined our sample space as it's some trial and one of these outcomes has to happen. So the probability of the empty set is 0. So what is the probability of an impossible outcome? That's not to be confused with this idea of what is the probability of nothing happening, because I can say, well, there's an event called nothing in my sample space, and I can assign it a probability, whatever probability is appropriate. So this is the probability of something that's impossible. Right, and we have to select something because of how we defined sample space and how we defined outcome. All right, oh yeah, so my animations are off a little bit as they do get at least halfway through the lecture, but so I have an event A. What is the probability of not A, or the complement of A, right? So this is complement of A. So my sample space is in some sense my universe, and I have an event A that is some subset of the items in the sample space. So in this case, not A would be everything that's in S that is not in A, basically. Technically, that should be called the complement of A, but I use not A interchangeably. And yeah, so the complement rule is, of course, if the probability of all of the elements in S is 1, and the probability of all of the elements in A is probability of A, well then everything that's left must be 1 minus this probability, right? So yeah, yeah, A complement is a subset of S, and thus it is an event. But we can use what we know of the event A to determine A complement. Since both of these, the union is equal to S, and they're disjoint sets, then if I add the probability of A plus the probability of A complement, I get the probability of S, which is equal to 1. And then I get to this, which should have been revealed a little bit later, but that's fine. All right, is that part? And yeah, I guess so this is called the complement rule of probability. And as with counting, it's sometimes easier to compute the probability of the complement of a set rather than the set itself, where the set is an event. All right, questions? Okay, so I have my sample space here, and let's say I have sets A and B, and they are disjoint sets. That means that, I might have some items in A and in S and in B, but an item in A cannot be in B, and an item B cannot be in A. So I know how to define the probability of event A and the probability of event B. However, these are just some set A union B if I put them together, which means I can define an event A union B, whose probability is the sum of the probabilities of event A plus the sum of the probability of event B, right? So really, this is simply another set. I just count, I sum up all of the probabilities of all of the elements in both of these sets. That's all I'm doing. So this is equivalent to the sum rule of counting, right? But now instead of, when we were counting before, we would say, well, each of these is worth 1, right? And then when we count up the total. But now we're saying each of them might be worth, well, I don't know, some value between 0 and 1. So the sum rule is the same, except instead of counting 1 plus 1 plus 1, we're counting whatever the probability function tells us to count. All right. Questions? In the event that A and B are not disjoint sets, then of course we have this intersection of the two sets. So to count all the elements, we would have used, right, if we go back to counting, we want to count everything in this set A union B, then it's all of the elements in A plus all of the elements in B. Well, then we've counted everything in here twice. So we're going to subtract all of the elements in there once. This is the inclusion-exclusion rule of counting. However, all of these are sets, and thus all of them are events. So when we convert this to probabilities, we can simply sum the probabilities, right? So this is, in some sense, it's analogous to counting, except we're counting whatever the probability function tells us to count. So the probability of A plus the probability of B, if I take all of those probabilities, I've counted the probability of these elements twice now. So now I'm going to subtract the probability of these elements in order to get the correct probability. All right, questions? So yeah, this is similar to the inclusion-exclusion rule. So I might refer to it as inclusion-exclusion of probability. I don't think that's the official title. That's just sort of what in order to communicate it more effectively. So similar to inclusion-exclusion, it's not actually called inclusion-exclusion, or at least not that I could find, but I will call it that. I'll just use the words of probability. Okay, so let's look at an example. Let's take the set S of all the numbers from 1 to 1000, right? And we'll say that the probability of each of these outcomes is equal to 1 over 1000. So they all have equal probability. And, you should be convinced that if I summed up the probability of each of these, that sums up to 1. So that means that all of the rules of our sample space have been obeyed here. So this is our sample space S. So we can choose a random element X in S, and we're going to say, what is the probability that X is divisible by 2 or 3? Okay, so now we have an event. Yeah, so now we have an event, let's call it E is X is divisible by 2 or 3. So this is an event and I can determine the probability of it, but it might be easier to break it down into 2 separate events. So this OR here, when I map, so this is of course a set. When I use OR, that usually implies a logical OR, which means that I'm going to take the union of these 2 sets. So I can say, I could take the set of all the elements that are divisible by 2, and then I can take the set of all the elements that are divisible by 3. And then I can take the union of those 2 sets as my event, right? So this event is equivalent to all of the elements in here. Of course, if we look at the intersection of these 2 sets, we have elements that are divisible by 2 and by 3. So an element that's divisible by both 2 and 3 is divisible by 6, right? Are we going to have cases of weighted probability? Sample 1 is probability 5, sample 2. Yeah, we don't really, mostly we focus on unweighted probability. So I'm trying to think if there's an example of weighted probability. As I said, we introduce probability here in the most general sense, but then we're really going to look at where everything has equal weight. Because the nice thing about when everything has equal weight is you can use counting in order to determine the probability. Okay. Any other questions? Example 1 is a probability of 5. Yeah. I mean, probably not this semester, but it's. I feel like I should maybe spend a little more time on that. Okay. Is everybody okay with this idea that if it's divisible by 2 and 3, it must be divisible by 6? Right. So that means I have a number B. There's a factor of 2 and a factor of 3, and then some other stuff. That means I can divide this number evenly by 2 times 3, which is 6. Right, so divisible by 2 and by 3 means it's divisible by 6. So now I have definitions of 3 different events. So I have event A is divisible by 2, event B is divisible by 3, and then I have event A intersect B is divisible by 6, right, which is this one. So now if I use the inclusion-exclusion principle of probability, I can determine the probability of, so this is probability of A union B, which is the probability of A plus the probability of B minus the probability of A intersect B by our inclusion-exclusion rule. So divisible by 2 is, well, I take each of them has a probability of 1 in 1,000. All of the even numbers in this set from 1 to 1,000, well, there are 500 of them. So if I sum them all up, I get 500 over 1,000. Just finding the lowest common denominator. Yeah. Yep. That's pretty much, well, not the lowest, but we find a common denominator in this 6. Yeah, if we take all of the numbers between 1 and 1,000 that are divisible by 3, well, that's 3, 6, 9, up to, 999. So there are 333 numbers in this subset. So this is set B, and set A is, of course, 2, 4, 6, up to 1,000. And there are 500 elements in A, and there are 333 elements in B. So that's where I get these two numbers. So summing up, 500 times 1 over 1,000 is 500 over 1,000. 333 times 1 over 1,000 is 333 over 1,000. Now, how many of these do I have? Well, so how many in this set? Let's move up here. So A intersect B is equal to 6, 12, 18, up to, is it 996? Or 998? I think it's 996. No, I don't know. Probably that's wrong. Something. Question mark, question mark. So if I divide 1,000 by 6, is it 996? Okay, perfect. If I divide 1,000 by 6, I get 166.66, right? So this is 1,000 divided by 6. So if I take the floor of this function, there are 166 numbers in this set. So yeah, I end up with 500 over 1,000 plus 333 over 1,000 minus 166 over 1,000. That's, probability of A plus probability of B minus the probability of A intersect B, and I get 667 over 1,000. So that's the probability of I choose a number that is divisible by 2 or 3. All right. Questions? All right. So we'll end there for today. It seems like, an appropriate place to end. So next, oh yeah, we have a class on Monday, so we will get into, it's not conditional probability, it's the, I don't know where my vocabulary has gone these days, but it's where everything in your set has the same probability, which is essentially what we've been doing, but we'll look at some more examples. And yeah, so these are all sort of applications of counting. But otherwise, I will answer any questions you have. And otherwise, I will see you guys on Monday.